Hello, so I was asked to do a video for the Pratt Truss, and I thought it might be fun to kind of show a little bit of background on this, of where it was developed first. So have a look at this. This is just out of Wikipedia, but it is kind of fun to see who made these original truss structures and why one was moved over another. There's a couple of problems in the back of your chapter if you look through the book, and this is actually the easier one. You can solve this with method of joints or method of section. So I'll let you decide which one you think would be easiest to use. And we'll go ahead and set this up in Excel, maybe try out a little of the goal seek or the solver to kind of skip some of the algebra for that too. For each of these problems, make a copy of it, just use your snipping tool, and then I'm going to draw which members are in compression and which are in tension just over here in PowerPoint using its drawing tool. So I'll go ahead and choose orange as my color for compression. So let's walk around and think about which one, and there's patterns that develop in a bunch of these truss structures that are very similar, that often when you have a bridge loaded from the top, you will have compression along the edge, the top uppermost part, and you will also have tension along the base. And you can think of starting these things with looking at the forces at the edge. If I compare the force at the edge to what is also applied going down, so this is, I would have to add FA plus FB plus FD, all of these forces above, and if it's symmetrical, I can just divide all of these forces above in half, and half of it would be on either side, but what's coming up from the ground is going to be a lot larger than what is coming down on it, so it's going to need a little bit more help to balance out those Y forces. So we'll have FA is going down, a little bit more help because this on the ground it's going to be holding up half of the structure. So we have this compressive arch happening along the edge of it, and then we're going to have tension along the base. So we can, maybe I'll make tension in green. Typically, if something fails, it's going to fail in one of the compressive members because it will buckle. Tension tends to be the very strong piece of it. So this is the part that you could actually replace this with a cable or a rope, and it would be stable. And that's often an economical way to build these, is to use cables. Let's see, some of these members are not doing anything. Let's go ahead and, considering what's happening right here at joint E, because there's no force hanging off of it, so this middle piece is going to have to be 0 because of what's happening at E. So I can balance the X forces here, but there would be no way to balance a Y force. So this has to be a 0. And anytime you see one of these T junctions with no other force hanging off of it, you know that's going to be a 0 member. Versus over here, so here's another T, but I have a couple of different members here to balance the Y forces. Okay, so that the outside edge is pretty easy to figure out, compression and tension. The inside piece, that one you can see is a 0 member. Where it gets tricky is deciding if these guys are going to be in compression or not. So let's go ahead and start with joint B. This is symmetrical, so it'll also apply to F. And if you think about what's coming up versus what is coming down, we have down, down. And so chances are we're going to have to help something hold this up. So I'm going to draw this in compression and make your best guess. Sometimes you don't know what it's going to be until you actually crank through the numbers of it. But if you crank through the numbers and you find the magnitude ends up being negative instead of positive, then you know you drew it in wrong. But let's go ahead and give it our best guess. And we're going to guess that this is going to be orange. So everything orange we'll call compression. And what goes down must come up. So let me go ahead and get my green highlighter out. So in order to balance the Y forces on this joint C here, I'll pull this up, which means this is in tension. And often this is another pattern you'll see is alternating bands of tension and compression. Okay, so once we have everything labeled in tension and compression, we know what our outside forces are. A couple more things we're going to need to worry about, and that is the angles. So we're going to need to break everything up in X and Y components, so we'll need to know whatever angles are going around here. For A, we can kind of look at just a giant triangle right here. So we have L1 plus L2 at the base. And then for our height, we will have our entire height here. And we can figure out what our angle A is at. For C, we will have a slightly different triangle. So let's do that in blue. Okay, so if we're trying to figure out what C is, let's look at this triangle right here. So the base of C is going to be L2, and then the height is going to be H. So kind of look around and identify those triangles so that you can make sure to get the right angles and sketch something out and actually label where those angles are so you don't mix up sine and cosine. Okay, once you have this, I'm going to go ahead and use my snipping tool and grab this figure and we'll pull it over into Excel. Okay, so here we are over in Excel. This is what was given for your homework. I'm going to go ahead and change those around just a little bit. So instead of 4 meters, we'll call it 4.5, and 3 will go to 3.5. But this will be close enough that it'll get you through that homework problem. Okay, I'm going to run around and figure out what my angles are here too. So for angle A, that's this yellow triangle. So I'm looking at the height is opposite that angle. L1 and L2 are the base, so equals A tangent. And I'm going to pull this off the table rather than type those numbers in so I can change these around later and check my answer. Okay, so there is my angle A is my height divided by base. And for B, it's going to be similar. But now we're looking at this blue triangle, right? So it's going to be the height divided by just my L2 on here. Okay, and we can turn those into degrees if that's how you think better, but we'll use radians for everything. So 17 degrees, this theta A is a little bit narrower than our, oh, I called that theta C. Let me switch that around. Okay, so there's our two angles. And now we have a choice of either using method of joints or method of sections. So what would you like to do? Let's go ahead and use method of joints. And I'm going to go ahead and make this kind of large, or I could just kind of zoom in on one corner. It's kind of nice to do some diagrams of each little piece of it so you can really think through what is happening on each piece. Okay, so I have joint A, start at the edge where you know the most about, and then work your way to the middle. So I'm going to add together the X and Y forces on each little pin of this thing. Okay, so here is joint A. So I can label some table, joint A, and I'll list all of the forces we have. So I have force A going down. So this is kind of the red force underneath. I have the force at A, the support that is going up. Alt 24 and Alt 25 lets you make those arrows. And then we also have AB, so I'll call this AB. And we have AC that is in tension along the bottom. And if you want, you can kind of color code this. So let's see, force. This is the red one coming down. Make that black again. And then the support, that would be this blue one coming up. AB, this is our member in compression, so we made those orange. And AC is our member in tension, so we made those green. Okay, so I have one that's just going to label everything, and we're going to have the magnitude of this, and then what's happening in the X direction and what happens in the Y direction. And all of these guys are going to have to add together to 0. So let's make just kind of a nice big table for everything. If I get this formatted, then for the rest of them, I can kind of take this table and copy and paste it around so that, but do a nice job so that you can, you can have a nice organized table that's color coded that you can then copy for the other guys. So eventually, everything in the X direction should add to 0, as well as everything in the Y direction. Okay, I'm going to go ahead and center that just because I like it to be centered. So what do we know so far? I'm going to zoom back out and we can start filling in this table for joint A. So we have the force at A going down, and I'm going to grab that from right here. This is in kilonewtons. And rather than calling it 4,000, I'm just going to leave it in kilonewtons. If you just leave everything the same unit the whole way through, just remember at the end, we're going to end up with kilonewtons here. And our force A, this is going straight down, so nothing in the X direction, and it is going down in the Y direction. Okay, the force at the support. We have to figure out what this is. So I'm going to make another one here, F support. And that is going to equal half of everything added up. So that's going to be equal 0.5 times, and we have FA and FH. So these are the two guys at the very end. And then in the middle, we have 7, 7, and another 7. Okay, so I could say 3 times 7 plus 2 times 4, but it's kind of nice to make sure I've got 1, 2, 3, 4, 5. I have all 5 of those forces accounted for. And it's symmetrical, and so I can just take 1/2 of that, and that's going to be what's happening up at the support. So here's my support. This is in kilonewtons, and this is in the Y direction, and it's going up in the positive direction. So then you can see what's coming up is larger than what's coming down. And because AC, so our member in tension, is entirely in the X direction, that means everything in the Y direction has to be balanced by our orange AB. So we can say equals negative sum of this stuff. Okay, so now we have what AB is. And if we have one piece of AB, then we've got all of it, right? So let me just draw that nice orange triangle. So we have AB is coming down in compression, and we know the Y component is going to be this -10. So then we can figure out what the X component is and what the total force is, because we know what this angle is, right? We know what this angle at A is. Okay, so if we say Fy is equal to F times cosine, and we'll just get the magnitude of this thing. So I'm going to take care of that negative sign, but the Y component, the Y component is the opposite piece. So that's going to be sine. Yeah, write out equations so you can kind of think through what you're doing here and make sure you have sine versus cosine. So then our force would be equal to negative Fy divided by sine of theta A. So I'll grab that theta right out of our table here. And then once we have our total force, then we can say Fx is equal to negative, it's going to the left, and that's going to be adjacent side, so you'll be cosine of this angle. Okay, so that means that AC has to balance the rest. So AC is going to be negative of what's happening on the compression. Okay, so now we have everything that's happening on this first joint A. Let's go ahead and copy a table down, and what joint should we do next? So if I zoom in on this, if I look at joint C, I don't know BC and I don't know CD. I don't know, there's three things coming off of here. I only have two equations, Fx equals 0, Fy equals 0. So I can only solve for two things, and I have three things I don't know here. If I look at what's happening at B, I know what FB is, I know what AB is now, and so for this one, I only have two unknowns. So let's go ahead and do joint B next. Okay, so here is joint B. So we have, let's just draw these guys in here. So this is AB that we already just solved for. And here is BC that is only in the Y direction. That'll make things easier to solve. And then we also have, we can call this BD. Okay, so our unknowns here, we're going to solve for what BD is and also what BC is. So here we go, edit copy. And let's go ahead and start a new table for a new joint. I'll go ahead and make this smaller. Yeah, for these ones, it's really, really important to draw pictures to keep track of everything. Okay, so I'll go ahead and just copy paste. And this time we will do joint B. So let me go ahead and just kind of clear all of this out. So once again, I have the same number of forces. I've got 4 forces. So I have FB coming down. So instead of FA, I have FB. So I'll go ahead and come up here. My FB is going to be, that's one of these 7s. And that is coming down in the Y direction. So that's this red force right here. I have BC, and I don't know what the magnitude of that is yet, but I can fill in this 0 because I know BC is entirely in the Y direction. Okay, for AC, I know AC, or AB, is compression, and we got that from the previous one. Now this time around, I'm now pushing up, so I will have the opposite signs as what I had before. So I'm pushing to the right and pushing to the left. This is this equal and opposite signs kind of deal. So yeah, make sure to draw pictures. So it's pushing down on A, but it is pushing up on joint B. So that's important. That's our compression member, our orange one. And then for BD, and actually BD is going to be in compression too. But it is now pushing down and over. So this one, I don't know. I've got a bunch of bunch of unknowns here. And what I can do, let me go ahead. I'm going to put the two that I don't know together, and we'll play around with goal seek. So I'm going to go ahead and insert a column and move this up here so that I have my two unknowns right here next to each other. I'm going to go ahead and so we have this guy that we want to go to 0, right? So we have adding the forces in x to 0 and y to 0, and maybe one of the things for goal seek or the solve is that it can get this to 0 by making one positive and one negative. So I'm going to change these around to absolute values. And this is, you can solve for this using algebra and by hand, but it's kind of fun to use Excel's solver just since we have it. And I'll let you do that for the test too. That's fine. Okay, so this will eventually be 0. And BC, what I'm going to do is I'm going to start by just estimating something. So I'm going to estimate BC is 10, and this is totally wrong, but I'm going to start with a guess. And then I'm going to link this over to here. If I did know the magnitude of BD, I know how that divides into X and Y components, right? So if I have BD going down, and I know what angle that's at, it's at the same angle that the other one was. So we have, it's going down in the Y direction, over in the X direction, and this is that theta A again, right? So it's going to be in the X direction, it's going to the left, negative of this times cosine. So here's the X component is adjacent. I'm going to come up, and do you see how it's at that same theta A? So make sure I'm grabbing the right angle here. And then for the Y component, that's opposite. So I'm going to say equals negative because it's going down, opposite. And for this one, it's the sine of this angle. Oh, I need to get a multiplication here. Okay, so if I did know what this was, then I could split it into X and Y components. And so really these are the pieces that I need to get these two numbers right. Okay, so what goal seek or solve allows me to do is to change these two numbers in order to get this cell to 0. So I'm going to go ahead and say I want this to be 0, and then I'm going to change those two to do it. If you don't have this solver tool in Excel, it is an add-in. You have to go to File, Options, and it's an add-in. So you click on Solver Add-in. This is the tricky part. You have to say Go. Go, OK. And then once that's in, then you can add it to your, so customize ribbon, and you can make sure that all of those add-ins are showing up in your ribbon. So there's a couple things to click on to get it in there, but it is a very useful tool to use. Okay, so here we go. I'm going to go ahead and open up my solver. It is more powerful than goal seek because I can change multiple cells. Okay, so set objective. So I'm going to say H24 needs to go to 0, or sometimes you have better luck if you just make it a minimum rather than exactly 0, because it might not be able to do exactly 0. And then for the solver, I can actually change multiple cell values. So it will plug and chug different values for each of these forces in until I get to that 0. So I'll go ahead and do that. And it'll say, is this close enough? 10 to the negative 6. That's pretty close, right? That's looking pretty good. So I'm just going to say, okay, that is close enough. I can even clean up the spreadsheet a little bit by saying I want a number that's just 2 decimal places. That should be fine. Okay, so here we go. This is, so now we have what the magnitude of BC is doing, and also the magnitude of BD, which it looks like these two guys are the same, and this looks like, let's just make it 7. So we have these two are equal and opposite, and these two are equal and opposite. And think about why that would be for a little bit. So whenever you have something that's kind of a little bit symmetrical around here, so AB and BD, they're going in the same direction. So they're going to want to balance each other out, and then the force coming down on B and up on BC, these are also in the same direction. So whenever you see kind of the symmetry going on, then you will often get kind of the same thing on either side. So that's, you'll see a lot of patterns as you start working through these more and more. Okay, so we're slowly walking through this thing. The last piece is to come here and look at the very top of this thing. And this is where we'll see if we did everything right. So we'll use symmetry so that what's coming up on the left and the right is going to be the same. So let's just label this. So I've got a red pen here. So in compression, this is BD. Yeah, label everything. That it's really easy to get stuff mixed up. So we'll say this has exactly the same magnitude here. DF is the same as BD, so we'll just say BD. And if you think about what's happening, that if the magnitude is the same, our X forces will cancel out nicely, but our Y forces here are not. Okay, so at the very end, we're going to have to make sure that what's happening in the Y direction is going to work out. Okay, so as well as BD, we also have these tension members coming down, right? So this is CD. And again, if you think about what's in tension, this is going to be symmetrical on one side to the other. And the X piece of these two guys is going to balance out. So we don't have to worry about the X side of it. It's the Y chunk. The Y chunk is what's going to have to balance out. So we will know that we solved all of this correctly when at the very end we have our Y forces are all adding to 0 here. So when this is where, yeah, this little pin right here is where everything is coming together. So, okay, here we go. Edit copy. And there's quite a bit coming together at D. We don't have to worry about the 0 force member. That makes it a little bit easier. But let's come down and do one more joint here. Okay, so for this guy, so we'll say this is joint D. And once again, I'm going to go ahead and just clear all of this out. We'll figure out so I have 1, 2, 3, 4. I'm not going to worry about the 0 force member. And I have FD happening at the top. Okay, so FD, let me grab that from the table up here. So here is my FD. And that is coming straight down at the top. I have BD. I'm going to call this BD on the left and BD on the right. So these are my compression members. So maybe I'll make them like orange for compression. And I can pull these off of our previous table. So here's our 35. I might actually, I'm trusting this number that we actually calculated a little bit better. So we'll say those are both the same magnitude, but they're going different directions. So the left-hand side goes positive, positive. So here's our left is positive, positive. And on the right-hand side, we're going up in the y direction. So this is the same. And we're going to the left in the x direction. Okay, so yeah, really draw those pictures. So you can see in the x direction, they cancel each other out. In the y direction, and they're doing a lot more than just the 7 coming down. So you can see just on its own, we're not going to be able to balance that 7. So here's where CD comes in, right? And I'm going to have to add one more row here. Okay, so I'll call this, and that is, let me make sure I wrote that right. So this is CD, and we'll call this CD on the right-hand side, or maybe I said left, and then CD right. Okay, so this is what we have in tension. And again, the X forces are going to cancel out. The Y forces are going to need to help this guy out. So if we think about what needs to happen here, so right now I have an addition of 14. So 10 plus 10, so this is 21. 21 minus 7 is 14. And it's going to be half of that in each of these, right? So it's tension, it's pulling down on each side, it's pulling equally down on each side. So I'll say equals negative half of what it takes to balance this, right? So I'm just going to add all this together, and half of it's going to be on one side, and half of it's going to be on the other side. So we set that up. Now we have 0. So this one, rather than using the solver, we can actually go through and get this last chunk of it, right? Because I know what that angle is. So if I take this thing, let me just draw it here. So this is our member in tension that is pulling down. So down in the y direction is what we figured out, and these x ones. And in this case, the angle was, let's see, we called it theta c over here. Okay, so this is theta c. So if we know one piece of this triangle, Fy equals F times sine theta c, then I can get the rest of it, right? So F is equal to, and we'll just go for the magnitude here, so I'm going to get rid of that negative sign, but we'll say Fy divided by sine of theta c, so here's that guy, theta c, and we have the same magnitude in each of these. So you can look at the x components are just going to balance each other out. So on the left, well, it'll be negative, so equals negative of this times cosine. We're on the adjacent side of theta c here. And the right-hand side is just going to be equal to the negative of that. So we have everything adding to 0. We have the magnitudes of everything going on in each of those members. And we've got nice tables set up for each joint. So thinking about this, we can use the member of joints, or if that gets super frustrating to you, you might try the method of sections too, right? So the method of sections, what we would do is maybe start with this chunk again, but for the next piece, we could just kind of chop it right down the middle, and we have 3 unknowns. So I could then solve for the tension pulling here, the tension pulling here, and then the compression pulling on it here. So you could look at this piece of it and make sure the forces and the moments balance on just this piece of it and walk through method of sections, or the order to work through method of joints is start at the edge, so this is 1, and then we're going to look at 2, then we came down and looked at 3, and then last you come up here. So, and we did it in this order because of the number of unknowns. So this one only has 2 unknowns coming off of it. After you solve for that, you'll have 2 unknowns for it. This one in the middle, there's 1, 2, 3, 4, 5. So that's definitely the last joint to look at in the middle. Okay, yeah, the hard part of that, make sure you have all the angles right, draw pictures, make sure you get sine cosine going correctly. And that is the Pratt structure.